Good morning. Today we're going to finish up on chapter 1. The goal will be on Friday to start chapter 2, so you should be reading up on the first few sections of chapter 2 on the exponential function. And homework. You also have homework that's due Friday. Now we're going to go over a few topics in the end of chapter 1 today, and then about halfway through the class we'll cover all the material. Then I'll open it up for questions on the homework, and then if there's any time remaining, we'll cover a few more things in chapter 1 that aren't on the homework. So that's the game plan, and let's begin. Okay, today I want to talk about moving fluids, and then you have to bring in the concept of viscosity. So viscosity, imagine you have a plate, say a metal plate that's sitting stationary. And above that metal plate, you have another metal plate. Both of these have area A that's moving with a speed V. You're pulling it, so it's moving. And in between the two plates is a fluid. Say water or some other viscous fluid. And the plates are separated by a distance L. So now what we want to do is we want to figure out what force it takes on that, to pull on that upper plate in order to keep it moving at a constant rate. You're not accelerating it, but it's not slowing down, it's moving at a constant speed. So we're going to take this to be the x direction and this to be the y. And so how would F, the force, what would it depend on? So what parameters in the problem do you think it would depend on? When would you need a bigger force? Pardon me?
When you have a bigger plate.
Bigger plate, so a bigger area. So the force is going to be proportional, in fact, to the area. The more area you have, the harder it's going to be to pull. What else is there going to be? More friction, and the friction is going to be a property of the fluid that's between the plates, and it's going to be, in fact, what's going to be called the coefficient of viscosity, usually given the Greek symbol eta, and this is the viscosity. See? Okay, so that really is a measure of internal friction within a fluid. What else? How about the speed? The faster you want this thing to go, the harder you have to pull. So it depends on the speed, and also it depends on the distance between them, because if you have a very small gap, you're going to need a very big force, where if the gap is huge, it'll be easy. So it turns out it's V over L. Now, whether it's, you might say, well, maybe it's V squared or square root of L, but this turns out to be empirically, if you did the experiments, how the force depends on these various parameters. Okay, now in general, if you don't have just this simple of an equation, but you want a general relationship to get the force per unit area from viscosity, so the frictional force per unit area, it's going to be the viscosity, and instead of V over L, you're actually going to get in the limit dV, D, and which direction? It's going to be in this Y direction, because that's the way L turns. So what you have is you're going to have frictional forces on a plate if there's a velocity gradient. And there's a velocity gradient in this case because the velocity starts, it's at rest down here, so as you go up, it gets faster and faster. The fluid gets faster and faster until it reaches the fastest point at the top. So there's a velocity gradient, which means that there's a derivative of the velocity in the v direction. So this is going to be our general equation for viscosity. We're going to try to find forces in the fluid on surfaces, really, and it's going to be velocity gradients that are really important. Now, it's kind of interesting to look at the units of viscosity. So now, if we look at the units, it's got to give us force per unit area. So it's got to give us a Newton per meter squared. But you divide this side by dV dy. So you divide it by meters per second per meter. So now, if you have this is the units for eta, you'll get newtons per meter squared if you multiply by dV dy. And you can simplify that a little bit. This comes out to be newtons. The seconds come up top. Meters squared has a meters cubed here, but then a 1 over meter, so it becomes meters squared. This is the units for viscosity. And interestingly, we don't usually give that some name of some scientist. Usually it's just written like this. So, what did we do last class? We wanted to compare the properties of the two most important fluids for life. That, first of all, water, and then air. So, the viscosity of air, so let's see, is about 1.8 times 10 to the minus 5 Newton second over meter squared. And the viscosity of water is a lot higher, as you'd expect. Water is much more viscous. It's about 100 times 10 to the minus 5 Newton second over meter squared. So water is a much more viscous medium. You have a much more difficult time overcoming friction in water than you do in air. And as you might expect, it has, yes?
Does the friction of air change regularly with height above sea level?
Good question, and I think it would, because this would probably correspond to about sea level. It's going to change with the air pressure, which will change with height. So, yeah, and it's also actually a very sensitive function of temperature. So these are sort of standard numbers, but it can depend on a variety of things. It can probably depend on humidity and other things too. So, I'm kind of presenting you just a simple round number for typical weather, typical situation at zero elevation, sea level. Other questions? If you're interested in viscosity and other properties of moving fluids, I'll recommend another book. Stephen Vogel has a book, Life in Moving Fluids. Doesn't have a whole lot of math, but some fascinating fluid dynamics from sort of a physiology and ecology perspective. So, Life in Moving Fluids, one of several good books Stephen Vogel's written. Okay. So the most important example of viscosity is going to be fluid flow in pipes. The main reason is because we're going to be looking at fluid flow through blood vessels, which are small cylindrical pipes. So the next thing I want to do is I want to take these ideas and I want to apply them to a pipe and see if I can learn something about fluid flow in tubes. So I'll erase this and we'll look at the flow in a pipe. Okay, so flow in a pipe was first studied by a Frenchman, so it's got this funny name, Jose Flow. Jose Flow is steady flow through a cylindrical pipe. So we have a pipe here. Think of it as a blood vessel. And it's got a radius, capital R, for the whole pipe. And this will be our x direction. And we're going to apply some pressure difference across the ends of the pipe. And we're going to try to understand the flow inside the pipe, including the whole distribution of fluid velocities. So the way we're going to do it is we're going to look at a small cylinder inside the fluid and find all the forces on it, kind of like what we did last class with the cube of fluid, to find all the forces and then develop a differential equation describing the forces. So here we're going to have a smaller, this is just a small piece of the fluid, and it's going to have a limit, or a length delta x, which we're eventually going to take down to 0, and it's going to have a little radius r, and we want to look at that and look at all the forces. So I'm going to draw a bigger picture of this down here, just so we can focus on this small bit of fluid. And now, you have pressure, a pressure gradient. So you're applying, say, a high pressure on this end and a low pressure over here, so there's a flow going in this direction. What's the force on this end of the pipe from the pressure? Well, we talked last class, what was pressure?
Force over area.
Force over area. So if you want to find the net force on this end of the pipe, you're going to take the pressure and you're going to multiply it by the area. What's the area of this end of the pipe? Pi r squared. So we'll call this x, and we'll call this x plus delta x. So there's a force here, P of x, the pressure, times pi r squared. But there's also a pressure down at this end. It's probably a little smaller since you have a pressure gradient driving the flow, but there's still going to be some pressure. And that's going to be a little bit farther along, so that'll be P of x plus delta x pi r squared. Now, last class we were looking in the vertical direction and the other force was gravity. But we don't have any gravity because this is horizontal. But we do have viscosity. The reason why this thing's not accelerating to the right is because there's internal friction, which is so it ends up going at a constant speed. What would be the force on the surface of this cylinder due to viscosity? Now, what did we just say when we developed the equations? We said force per unit area was going to be eta times dv derivative of v. In this case, it'll be r. It's the direction perpendicular to the surface. That was the force per unit area, but we'd have to multiply by the area to get the total force. So now, what's the area of this? If this was a pop can, what's the area around the pop can? Not the end caps, but this other part. What would that area be?
2 pi r change in x.
2 pi r delta x. And the way to see that, if you don't see that immediately, well, first of all, 2 pi r is the circumference. Delta x is the length. So if you took this cylinder, which had a radius r, and you cut it and you set it out flat, well, this side is going to be this, what was the circumference, 2 pi r, and this side is going to be the delta x. So your area would be 2 pi r delta x. All right, now, this is in steady motion. We're assuming this is in steady motion. It's not accelerating. So F equals ma means that the acceleration is 0. So the sum of the forces is 0. Last class, the sum of the forces were 0 because things were stationary. This class, they're moving, but they're not accelerating. So the sum of the forces is still 0. So we have, let's take direction. This force, by the way, keeps this from accelerating. So it's a force, it's a frictional force. It's opposing the motion. If the flow is going down this way, then this would be a force opposing the motion. So P of x pi r squared, positive, minus P x plus delta x pi r squared. And then this force is minus eta dv dr 2 pi r delta x equals 0. So we got the sum of the forces equals 0. Now, what did we do last class when we were looking at the hydrostatic forces? We got to this point, and then we decided we were going to look at things not just at forces, but what? Do I remember? We divided out by the volume. So we're going to look at forces per unit volume. So let's just divide both sides by the volume. And the volume of this thing is area, pi r squared, times distance, delta x. So we're going to divide top and bottom by 1, or we're going to divide both sides by pi r squared delta x. All right, we're going to do something else also. We're going to write this term first, so it'll be a minus. We're going to get a p x plus delta x. When we divide by pi r squared, that's going to kill off this pi r squared. But we're going to have a delta x downstairs. And this minus sign's out in front of everything. Now there's this term. Since we brought a minus sign out, we're going to get a minus p of x. Those are those first two terms, dividing through. And then we're going to get minus eta, viscosity, times, okay, you got 2 pi r here, you got pi r squared. So you're going to keep the 2, the pi's will cancel, and you get a 1 over r. So you get 2 over r times, we got rid of the delta x, but you have a dv dr equal 0. Okay, one last thing here. We have move this to the other side, and as delta x goes to 0, what do we have? What do you have? What do you have as delta x goes to 0? Well, you have infinity, but up here you have something that's going to 0. So that's the derivative. That's the definition of a derivative. As delta x gets small, this becomes the same as this. You take the ratio, so this becomes the derivative minus dp dx. So if you move it to the other side, you get dp dx minus or equals minus eta 2 over r dv dr. Or in other words, dv dr equals minus r over 2 eta dp dx. And that's our differential equation. And it's a little more complicated than the differential equation we had last time. Now the good news is you can usually think of this pressure gradient as just a given function. You apply some pressure gradient across the ends of the cylinder. So we aren't really solving for P. We're assuming P is given. The pressure, how the pressure changes with position. This is really a differential equation to give you the speed as a function of R. All right. So any questions on how I got that differential equation? Now, in this class, we're not going to make this class all about solving differential equations. What we want to do is we want to use my favorite method for solving differential equations, and that is guess a solution and then stick it into the differential equation, check it, maybe find what some parameters equal. So, here we go. I'm going to erase this derivation now so we can solve it. So, last chance if anybody wants to question. Yes?
So, according to that equation, there would be different rates of flow depending on if you were at the edge of the tube or in the middle?
Yes, different velocities of the fluid, depending on whether you're at. In fact, what we're going to find, just to jump ahead, is that you have this sort of velocity distribution.
Yeah.
Much larger in the center, going down to the edge.
And so that would be assuming if there's the same force on all the different areas. So I'm trying to think of like a problem where this would practically be the case, because usually you're going to have like, I don't know, a round piston pushing and not letting any of the fluid flow at different rates. You know, it's just pushing all the fluid.
If you had the plug flow, is what that's called, then that's a different situation. You have something, a piston is pushing it. We're really looking at water or blood flowing through a tube, and so this is just a little element of the water. This is just a little element of the water I wanted to focus on, but it's not an object inside the fluid. It's a little element I'm trying to calculate the forces. So this would be moving along quickly, the water or the blood quickly at the center and slower on the edge. So this is the way, if you apply a big force, big pressure gradient to the tube, this will develop, and in a short time it will develop this sort of flow with this velocity gradient. And it's the only velocity gradient that really gives you the proper balance of frictional forces in order to, because this area, think of the area, increases as you get bigger, and so you need larger velocity gradients in order to balance that. So you have a big velocity gradient here and really zero right at the center to get the viscous forces balancing correctly. All right. So let us now look at this. Okay, suppose I asked you I want to find V of r. I want to find the velocity as a function of r. this differential equation says I'm going to take some function v, I'm going to differentiate it, and I'm going to get something proportional to r. So what sort of function gives you, when you take the derivative, with something linear in r? Well, we could integrate. You could just integrate this. That's another way to do it. I'm not good at integration, so I like to guess the function and then differentiate it and check, which is kind of a backwards, dopey man's way of doing integration. But what, just in general, what function, if you differentiate it, gives you, if you had a function of x, and I ask you what function, when you differentiate it, gives you something proportional to x? Yep. X squared. So in this case, we would make a guess. So this is our guess. V of r is going to be some function, some constant a times r squared. That looks promising because when I take the derivative, I'll get something proportional to r. But you could also have a constant. You could think of this as a constant integration, or you could just say that if I took a constant and I differentiated it, I get 0, so I get a term tacked on. Maybe it's necessary. So I'm going to guess this solution. With A and C, we don't know yet. This is going to be a general theme, what we're going to be doing in this class. We're going to make a guess for a solution, and sometimes the guess requires a little bit of insight. I wouldn't be expecting you to be able to guess some really strange function, but in this case, it's fairly obvious. And then we're going to plug it in and see what A and C are. So if we take this function and we have to take the derivative of it. So the derivative of r squared becomes 2ar, and the derivative of c is 0, equals minus r over 2 eta, and for our purposes we just treat dp dx as a constant. It's the pressure gradient. And now the r's cancel. So that's kind of what we're going for, because we didn't want this to depend on r. We want to just figure out what a is. A is a minus, and the 2 comes down here, r over 4 eta dp dx. So we're halfway there. Oh, excuse me, the r's cancel, and you get 1 because the r is going away, and the 2 came down. So we're halfway there. We know what a is. How are we going to get c? Anybody want to offer a suggestion of how we get c?
Initial conditions.
Almost. Initial conditions you'd use, if this was a function of time, you think of it as initial conditions. What do you use when you have functions of space, like we have, function of r? You use boundary conditions, conditions that are at the boundary. And we're going to assume that this cylinder, this blood vessel, is stationary. And so what we're going to use is what's called the no-slip boundary condition. When fluids flow next to a stationary object, if you look right next to the object, the frictional forces keep the fluid from moving at all. So you have a very thin layer where fluid flow goes to 0. You might say this isn't real obvious. That would mean the air's no air motion at the floor here because the floor is stationary. And actually that's true. It turns out that when you're looking at low viscosity fluids like air, there will be a large pressure gradient right near the surface. But if you look right at the surface, you don't have any sort of air motion right next to the stationary surface. You don't have any motion of the blood right next to the surface of the tube. So that says no slip boundary condition says that V at the surface, and the surface is at little r equals big R. When little r equals big R is going to be 0. All right, so we can say that V is 0 when little r is big R. We already know what A is. A is this thing, minus 1 over 4 eta dp dx. And this is r squared, which we're evaluating at big R because we're at the surface. That's where it's 0. Plus c. Our no-slip boundary condition tells us that when little r is big R, V is 0. And this can give us c. So we find that C is equal to 1 over 4 eta dp dx r squared. Well, now we have it. We have both A and C. Again, you could have gotten this by just integration if that's your thing, but you still have to apply the boundary condition. And so now we can plug these back in for A and for C, and we just get our equation for V of R. Okay, both of them have the same thing out front. 1 over 4 eta dp dx. And this first term has an A as a little r squared, but we've got a minus sign in front of it, so we're going to actually put that second. We're going to put the C first, which is just capital R squared, so you get big R squared. That's the C term. And then this term is going to be a minus little r squared. And that, we found, is the entire velocity distribution inside the tube. So this is Poiseuille flow. So it really does have this shape. If you looked at this, if you looked at velocity as a function of r, little r, it goes from 0 at the center out to capital R. What's the velocity at the center? It's going to be the maximum. So when you're at the center, little r is 0, and you're going to get at the center, let me move this up out of the way, it's going to be 1 over 4 eta dp dx times big R squared. That's the velocity at the center. What's the velocity out at R? 0. That's the no-slip boundary condition. And that works because when little r equals big R, these terms cancel. What is the shape that connects these 2 points? What's that shape? Big R squared minus little r squared. That's a function of R. It's going to be a parabola, upside down parabola, because it's got the minus sign. So something y equals x squared is a parabola. So it's going to be an upside down parabola. It's going to look something like that. And that's going to be the velocity distribution. It's going to be big in the center and fairly uniform, and then it's going to be 0 at the edge. So that was our goal, was to find that. We're going to look at some other things having to do with this Poiseuille flow, but this was our first case of actually solving this differential equation with the boundary conditions. Questions on that before we go on? There's one more thing I want to do. Sometimes you're not interested so much in the velocity distribution. What you want to know is the net flow through the tube. How much total blood is flowing through the artery. Okay, to get that, we're going to have to look at flow. So I'm going to erase this stuff again. I'm going to keep my solution here. I need some more space, so get rid of this. Okay. Flow. Flow is going to be how much? How much volume per unit time? So what we're going to do is we sometimes call that little I. It's a symbol. And flow is in general area, cross-sectional area times the speed. See, does that make sense? Area is meters squared. Speed is meters per second. So you end up with meters cubed per second. Volume per unit time. So that's the amount of volume per unit time going through the tube. Yes?
Is it okay if we use volumetric flow rate? If we learned it like that before?
I mean, how is that? Isn't volumetric flow rate essentially the same thing?
It's the same thing.
You could use the word volumetric flow rate if you prefer. I, preferring short, simple words, just going to shorten it to flow. But it's volumetric flow rate if you prefer. It is meters cubed per second. How much total flow is going down the tube? Now, in general, suppose you had a pipe that necked down like this. You can use a continuity argument. the flow going down any spot along the pipe has to be the same. If it wasn't, blood or water would be building up. It would be, if you had more water coming down, more liters per second coming down from the left and leaving from the right, then you'd either have water piling up in the center or you'd have creating a vacuum in the center. So you really have a continuity. You have to have the same flow rate everywhere along here. The pipe, basically all the positions along this pipe are in series. So if you have a small, remember the flow is area times speed. For a large area region here, you have a slow rate, but you go through the center here, you have a faster rate, and then it's going to slow back down. The way to think about it is, this is the river. This is a river, it has a flow coming down, and you have to have the same flow rate, volumetric flow rate everywhere along the river, otherwise water would be piling up. And so where the river narrows down, that's the rapids, where the water gets going really fast. And this is the wider area of the river where it spreads out. So basically, you have a continuity equation that says the flow has to be area times the speed. So what I want to do is I want to calculate the volume flow rate through this pipe. Problem is, this works great if the speed's constant across the area, but if the speed's not constant across the area, you really have to replace this by integral v speed integrated over the area. So if you had a river where the flow was different here, then here, then here, then here, you'd have to integrate across the whole cross-sectional area. So that's what we're going to have to do because we know the flow is different at the center than at the edge. So we're going to have to integrate across this flow. So now, a little bit of calculus here. We have to integrate. We know the speed only depends on R. So let's take this pipe and let's look at it from the end. So we're looking down the end of the pipe. This is capital R. We know that the speed is uniform at all along any place in the pipe that has the same radius. So all through, if it's the center, this is little r, all through this region, the flow is the same. It has the same radius. So we can just say that the flow through this small region is just going to be area of that times the speed. And then we're going to have to integrate for different values of r from 0 out to big R to get the total flow. So what are we going to do? We need the speed. Well, we went through a lot of effort to get the speed, so it's right here. 1 over 4 eta dp dx r squared minus little r squared. So this is the constant. This is just the radius of the tube. This is the area as we're changing the area. We're going to integrate over this little r. How about the area of this region? Its thickness is going to be dr. What's the area of that thin region? What would be that area? Okay, suppose you took it and you cut it and you stretched it out into a straight line like this. Well, its thickness is still dr. How long is that?
2 pi r.
2 pi r, that's the circumference. So you're back to circumference times thickness. So the area here is going to be 2 pi r dr. That's the integral we're trying to do. All right, so this seems a little complicated, but that's really the hardest part of the calculus is figuring out how to integrate over this end. Let's just do it now, and you won't be asked in an exam to do an integral over an area like this. Maybe in a homework, but not in an exam. So, 4 eta, the p dx, and the 2 pi, they're all constants. So I'll bring the 2 out, and it'll cancel one of the 4s, so I'll get a 2 eta and a pi and a dp dx, all outside the integral. What are the limits of the integral? I'm going to start with a really small little region, so it goes down to 0, and it goes out to capital R. So really I've got two terms here now. I brought the 2 pi out, I brought all this stuff out. Bring the pi out, brought the pi out. I've got 2 integrals, one here and one here. So let's break it up into 2. Okay, big R is a constant. So I've got an integral. The only R is this little r that's sitting out here. So I'm going to integrate r dr. How about the other integral? What's this one going to be? Give me help there.
R cubed.
It's going to be r cubed. There's no big R to take out front, but you're going to get an r squared and an r, so you get an r cubed, and you can still have the integral cubed dr. So we're almost there. We have to do these integrals, but these integrals aren't particularly hard. Pi over 2 eta dt dx. Okay. Integral of r.
R squared over 2.
R squared over 2. At the upper limit, it's going to be big R squared over 2. Lower limit, it's going to go to 0. So you have an R squared over 2 times R squared out front. You have R to the 4th over 2 minus integral of R cubed. R to the 4th over 4. At the upper limit, it's going to be R, big R to the 4th over 4. Lower limit goes down to 0. This is just R to the 4th. It comes out a half minus a fourth. A half minus a fourth is 1/4. 1/4, and you got a 2 here. So let's just write it. You're going to get a pi. The 4 and the 2 is going to give you 8 eta dp dx times r to the 4th. And what we have is we've calculated the total flow through the pipe. Okay. Now, why is this important? What's important is it goes as the 4th power of r. That's very sensitive to r. That means if you double the size of the tube, you don't double the flow. You don't quadruple the flow. You go 2 to the 4th. You make the flow 16 times larger. So when you have flow through a pipe, this viscous flow through a pipe like this, it's extraordinarily sensitive to the radius of the pipe. This is what happens in your blood vessels. In your blood vessels, your vessel changes a little bit, and it will change the flow by a huge amount. That is why the arterioles in your body have smooth muscle around them that can adjust the radius of the arteriole, and they provide. There's other vessels that are in series with it, but they provide a lot of the resistance. So these arterioles just change a little bit, and lo and behold, you can adjust the blood flow to all the different tissues quite effectively because of this very strong dependence on R. All right, so problem 1.40 in your homework. So I promise you we get to talking about the homework. Problem 1.40 in the homework says equation 1.59, which is basically this equation, relates the resistance of a vessel to its radius. Okay, well, essentially the resistance is going to be everything without the pressure gradient, because the resistance you can think of as flow is resistance times pressure gradient. So basically the flow. The flow varies as the 4th power. In a circulatory system, the resistance of the arteriole increases when smooth muscle radius surrounding the arterioles contract. By what factor does the resistance increase if the radius decreases by 10%? So smooth muscle contracts, the arteriole goes down by 10%, say from 10 microns or 20 microns to 18 microns. By what factor? Well, you're just going to have to figure out by what factor R changes. So if the change was by a factor of 2, you take it by half of its original value, and then you just take it to the 4th power. So the actual calculations in problem 1.40 are very small. It's just a matter of figuring out exactly what's one. You're using this fact that R to the 4th is how the flow varies. So the bottom line is just a 10% dip change in the radius of the arteriole is going to make a big change in the flow. Okay. Now, another homework problem. This one's actually not in your homework assignment, but I wanted to talk about it before we do other problems in your assignment. Is problem 43. Problem 43 says, suppose a student asked you, how can blood be moving more slowly in a capillary than the aorta? For an incompressible fluid, when the cross-sectional area along the pipe decreases, the velocity increases, so the volume current is the same. We just talked about that. That's the river rapids effect. The capillary has a much smaller cross-sectional area than the aorta. Therefore, blood should move faster in the capillary. But it doesn't. If you look on table 1.4 in the book, you find that the blood flow in the capillary is much smaller than it is in the aorta. What's the explanation? Yes?
All the capillaries are in parallel.
There's lots and lots of capillaries, and they're all in parallel. So what you really want to take into account is the total area of all the capillaries. It's as if your river didn't narrow down into one path. It kind of broke up into a whole bunch of paths. And you want, the question now is, what's the area of this path compared to all these added up? And it turns out that there's a lot of capillaries. You're going to find out in your next homework problem. And when you add up the total area of all these capillaries, it's much greater than the area of the aorta. So yes, the blood does slow way down in the capillaries, which is good because there has to be time for diffusion to happen. We'll talk about it in chapter 4. Diffusion of oxygen to get to your tissue. And if the blood was just zooming through those capillaries, there wouldn't be time for diffusion to happen. So it's good that the blood goes very slowly. Okay. Problem 42. Now this one's back to your homework. So another problem from your homework. The velocity of blood in the aorta is 0.5 meters per second. That's almost straight from the table for 1.4. And the velocity of blood in a capillary is about 0.001 meters per second. In other words, about a millimeter per second. Capillary is about a millimeter long, so it takes about a second for the blood to go through the capillary. We have only one aorta with a diameter of 20 millimeters, but many capillaries in parallel, each with a diameter of 8 microns. Estimate how many capillaries are typically open at any one time. Okay, so what you're going to do is you're going to say, here's the aorta, and you can calculate you're given everything to calculate the rate of blood flow through the aorta, and you can given everything you need to calculate the rate of blood flow through one capillary. The only thing, and you're not going to need to use this Poisson flow, you're just really going to need to use area times speed is the amount of blood flow. And they have to be the same, so you have to, there's n of these capillaries, so you multiply, divide the two flows to get n. So you're just going to try to estimate what n is from the blood flow through the aorta, one of them, and the blood through the capillaries, n of them. That is homework problem 42. If you find yourself going through very complicated calculations, you're probably on the wrong track because it's meant to be a fairly easy calculation. You should get a whole lot of capillaries. I won't say how many. Okay, questions on those problems. One problem left, and that's the hardest problem in the homework assignment. Problem 33, called Murray's Law. So I am going to erase this stuff and talk about problem 33, and then you'll be ready to do all the homework. Okay. Murray's Law talks about branching networks. So you have one tube that we'll call the parent, like the aorta, and it branches into daughter tubes. So these are two daughters. And we're going to always assume the two daughters are identical, so we don't have to worry. But it doesn't have to be, but for this problem, we can assume the two daughters are identical. Now, we just convinced ourselves that the flow in the parent has to equal the sum of the flows in the daughters. I mean, that's the whole idea of the flow splitting up. So the flow that comes down here has to split up. Half goes this way, half goes that way. So you get I from the daughter 1 plus I from the daughter 2, but we're assuming the two daughters are the same, so they're going to have the same flow. So you get 2 times daughter, parent, daughter. Okay, and we know what the flow is inside these pipes. Now the problem is, we don't really know, the PDX might change, might be different. So the PDX is different in parent and daughter. That's what makes the problem hard. Otherwise, we can just set this equal to this with different radii, cancel everything out, and we'd be all set. What we ultimately want to get is a relationship between the radius of the parent and the radius of the daughter. But we don't know how dpdx goes. So the problem says, suppose that there is something that's the same in the parent and daughter. Suppose it is the shear force, the shear stress, really, force being area. So suppose force being area is the same in the parent and daughter. And you might say, why is this? Well, we're going to assume the way that some animals developing, the way that it decides how big to make vessels is the vessels grow until the shear stress reaches some threshold value, and then it stops growing. So that means all the vessels are going to grow until their shear stress are all the same. Not their speeds, not their flows, but shear stress. Okay, so what you're going to have now is you're going to say the parent, which is going to be total flow, which is going to look like this, and you're going to have the daughters, which is flow that looks like this, but your dpdx is going to be different, but you're going to find the shear stress. How are we going to find shear stress for a flow in a pipe? Well, shear stress was eta dv dr. That was force unit area, which is really what we're talking about, shear stress. So we're saying that eta dv dr is the same in all the pipes. And eta is the same everywhere. That's just the viscosity of blood. So we're saying dv dr is going to be the same at the surface, at the blood vessel surface, because apparently there's some sensor in the blood vessel wall that senses this shear stress and then adjusts the growth of the vessel. Now you might say, oh no, the velocity is 0 at the wall. Well, the velocity is 0, but the derivative is not 0. So what you need to do is you need to find dv dr, take this equation, differentiate it with respect to r. The result is evaluated at big R. So you take this, differentiate with respect to little r, and then after you did the derivative, you put in for little r, big R, and that's going to be the same in both the parent and the daughter. So you're going to use this conservation law, you're going to use this for IP in the parent and the daughter, but you're not going to know what dpdx is, but you're going to be able to eventually solve this and get dpdx in parent and daughter from this relationship. And that's going to allow you to get a relationship between the parent vessel radius and the daughter vessel radius. So your final result is going to be something like you can find, your parent vessel radius is equal to some function of your daughter radius. And that's what the problem is really asking for, is that relationship. So like I said, that's the hardest of the problems. Now, I realize that you could probably check your work on this by Googling Murray's Law, because that's what the problem is really about, something called Murray's Law. But I want to see how you derive it from this basic idea that the shear stress is the sensor. It's the way that animals decide how big to make their radii. And it's actually true that a lot of vessels pretty closely obey Murray's law. If you look at blood vessels in the body, they get smaller and smaller with each generation as they branch and branch and branch. And each branching is basically following Murray's law. And also in your airway, the lungs, your airways tend to branch and branch and branch. And it also roughly follows Murray's law. So it's a useful little insight in how biology works. Okay, now we've had a chance to talk about all the homework assignment. The first two, problems 2 and 6, were estimation problems like we did in the very first day of class. 7, I guess 7 must have been, no, 2 was an estimation problem. 6 and 7 were biomechanics problems like we did in the second day of class. 16 and 17 were hydrostatics problems like we did last class. 33, 40, and 42 we just talked about. This Murray's Law is 33. Does anybody started the homework problems and have any questions now that you want to ask? Now is your chance. Yes?
For 16A, did you want like a specific height or just in terms of age?
For 16A, let me see exactly how it's worded. A lot of the times it depends on how these problems are worded.
Just the water. Just water.
Person standing erect. So you're going to assume, this is going to be asking you an estimate, you're going to have to make a guess at how tall the person is. And then you're going to calculate the actual pressure difference. So the answer is going to be some pressure difference in either atmospheres or torrs or pascals.
Okay, so
But you're going to have to estimate typical height for a person. So I'm not going to be worried if you estimate somebody's a little tall versus somebody's a little short. If you give me a height of 1 millimeter, I'm going to say, oh no, that's not a person. But as long as you get something reasonable, anywhere between Michael Jordan and that little guy in Game of Thrones, anywhere in that region, you'll be okay. Other questions?
It says like the human body is approximately a column of water. So should we use the density of water or density of blood?
You use the density of water, which is very close to the density of blood. But if the problem tells you to assume it's a column of water, so you can just use density of water. Yes?
For number 17, it says the pressure is 5 over above atmospheric pressure. Does that mean we're still in the atmospheric pressure, or your number is just 5?
The number is just 5, because atmospheric pressure is going to be pushing on your bag of saline, pushing on the body, so it's everywhere. So the pressure differences don't need to include it. So yeah, if you get a solution that's like 10 meters in height, that's probably because that would be if you assume the person was in a vacuum. But by assuming the person is in air, the pressure difference is going to be defined for.
For problem 2, should you find the length for one copy of DNA or both copies?
Both.
Both copies.
Other question? Yes.
Same problem. With the DNA, it says to wrap it into a sphere. Can you just wrap it end to end? Or
No. It's a ball of yarn. You take the DNA and you start wrapping it up into a solid ball of just like it was going to be a ball of yarn. So that's really what it is inside your nucleus. This DNA is wrapped up in all kinds of funny ways, but it's a little solid sphere when you end up in there being a nucleus. Other questions? All right. Now, if you still have questions, you can always try to email me. If you email me late Thursday evening, I'm probably not going to see it until Friday morning when it's going to be too late for you. Although I might be able to answer Friday morning. You might be able to get something done in 10 minutes before class. But basically, try not to email me late Thursday night about a homework assignment due Friday. But I will try to answer questions over email. It's a little harder to do sometimes if I can't see your assignment. But we can try our best. Now, let us talk a little bit more. We got a few more minutes about some topics that aren't on the homework, but are still important for fluid dynamics. All right, so we're going to no longer talk about Jose flow, but I want to talk in general about flow. Now we assumed that the fluid in the pipe was moving at a constant speed. But you can also have fluid that moves around and accelerates, F equals ma. So there's really, if you apply a pressure difference to your fluid, you can have one, resistance because of internal friction or viscosity, and you can have two, movement of the fluid and it's accelerating in something called convection. And there's a number that's defined as the Reynolds number, which really measures those two effects. Curly RE is usually the symbol. And it's going to be a measure of convection versus viscosity. And really what I mean by that is the convection, it would be the mass times acceleration part of F equals ma divided by the force of viscosity of F equals ma. I'm not going to derive how you get the Reynolds number because we just don't have time, but I'm going to give you the standard result. It's going to be density, speed, distance over viscosity. So rho is density, the density of the fluid. So if we're talking about things moving through water, it's the density of water. Eta is the viscosity of the fluid. L is a typical length. So if you're talking about a sphere moving through a fluid, it'd probably be like the radius or the diameter of the sphere. This is one of the difficult things about Reynolds number is that it's not always clear what typical length you should take. But it's some length characteristic of the problem, and V is some speed characteristic of the problem. Now, if the Reynolds number is really big, that means convection dominates over viscosity. You can almost ignore viscosity, and you're going to be having fluid that's accelerating around. You get all kinds of interesting things like turbulence, and it's like when we swim in water, which we see if we swim, eddies form and things that looks kind of turbulent water around us. That's a high Reynolds number flow. If the Reynolds number turns out to be really small, viscosity dominates. In which case, it's like swimming through molasses. All you can do when you try to swim is you're pushing on the fluid. As soon as you stop pushing, you stop moving. You don't glide at all. It's just constant sort of terminal velocity that you're going to be going as long as you keep working on it. Very different types of flow. So problem 1.51, which is not in your homework assignment, but if I made the homework assignments larger, it would probably be one of the first to be added. I want to look at the Reynolds number for a couple different cases. First of all, an eagle flying through the air. Okay. We're going to be talking about differences between air and water and between different life forms. So let's see now what the Reynolds number is for the eagle. Well, we have to know some data about the eagle. The speed that the eagle flies is about 20 kilometers per hour. You can do this conversion. I'm not going to take the time to do it, but you can convert that to meters per second to use in units because you want to have this to be in MKS units. That'll come out to be 5.6 meters per second. Now, is that a big speed or not? Well, it's pretty good. It's kind of from here to the window in 1 second. I don't usually go that fast, but if you look at Mr. Bolt, he runs 100 meters in 10 seconds, so that's half of his speed. So it's certainly a doable speed. Also, an eagle has a pretty big wingspan. A big eagle, you take your typical distance as its wingspan, about 2 meters. So let us calculate the Reynolds number. Density. It's the density of air. 1.2. I won't put in all the units. The speed, we just calculated 5.6. And its wingspan, typical distance is 2, divided by the viscosity. And I gave you at the start of class the viscosity of air was 1.8 times 10 to the minus 5. And if you do that calculation, you get 750,000. Now, one of the interesting things about Reynolds number is it's dimensionless. It's basically an MA term, mass times acceleration, divided by a force. So the units all cancel out. So it's a dimensionless number. It's a lot bigger than 1. So an eagle flying in the air is a really high Reynolds number type of a situation, where eddies and turbulence and everything dominate. Viscosity is almost negligible. Okay? Imagine we compare that to E. coli bacteria. Okay, E. coli bacteria swim around in water. They have a density of 1,000. How fast do E. coli bacteria go? Well, they go about 10 microns per second. If you were looking at a little E. coli bacteria, they have a little spiral thing on them that they can swim, but they go about several of their lengths per second if you watch them under a microscope. So the average speed is about 10 microns per second, which comes out to be, for the speed, 10 times 10 to the minus 6 meters per second. So they're really slow compared to the eagle. And they're really small. You might remember how big E. coli bacteria are?
1 micron.
1 micron is a pretty good guess. I used 2, which is their length, but Reynolds number, you're really trying to just get orders of magnitude. So 1 or 2, I'll use 2, so I have my notes, times 10 to the minus 6, because it's microns. Divided by, and now water is a little more viscous, so we had 100 times 10 to the minus 5 for the viscosity, which is 10 to the minus 3. And if you calculate that out, well, this 10 to the minus 6 and this 10 to the minus 6, that starts driving things down really small. So the Reynolds number comes out to be 0.00002, dimensionless number, which is a lot less than 1. So bacteria live in a much different environment than eagles. They live in a very high resistance viscous environment. So as long as the bacteria swims, it can make a little bit of progress. If it stops swimming, it stops moving. There's a fascinating paper, which I'm going to send you. It's not required reading, called Life at Low Reynolds Number, which really looks at some of the implications of this sort of living at this low Reynolds number. It's very non-intuitive to people, because people, when they're moving in air or when they're swimming, are moving around in fluids that are basically like the eagle, a fairly high Reynolds number. So our intuition is all geared to high Reynolds number flows. And so thinking about a low Reynolds number flow, like what bacteria have to face, is a very sort of different way of thinking about the world. And I will send you that paper in case you enjoy it. Okay, I was also hoping to get to a problem about how sap goes up trees. I don't think we're going to make to that this semester because we're out of time, and I want to move on to Chapter 2 next class. But if you're interested, problem 1.34 is not in your homework, but an interesting problem if you're a botanist and you want to figure out how in the world you get water up to the top of a giant redwood tree, because it's got to go up there in order to do photosynthesis. It's a long ways up, 100 meters up. That's an interesting question, and I will just leave it at that for the moment. But that's it for today. Homework due on Friday. We'll start Chapter 2 on Friday. I will see you then. Okay.
It was too late.